Good day, folks. Welcome to my YouTube channel. Today we're going to look at the question in work energy and power. It's a hot air balloon. It's a very interesting question. Guys, please don't forget to subscribe on my YouTube channel, like the video, watch my videos till the end. We're on a road to 2,000 subscribers. Thank you so much, guys, for the support. Continue doing the right thing. Let's look at the hot air balloon question. It says, a hot air balloon of mass of 245 rises from the ground on a windy day. The wind blows in the direction as shown in the diagram below. This is the hot air balloon is moving up and the wind blows it that way. This is the force that the wind exerts and at that angle of 50. It says with a force of 1870. So this is the force of the wind, right? 1000 at an angle. You need to keep that in mind. The hot air in the balloon provides an upward force of 3000. So the hot air balloon is propelled by the force that is going up, which is 3000, and causing the balloon to rise 12 meter vertically upwards at a speed of what? Of 15 meter per second. Guys, it's very important to understand what are the forces acting on the hot air balloon. So there's a force, the force that moves the hot air balloon that is going upwards, and then we have the gravitational force, and we have the force of what? The force of wind. The force of wind that is going in that direction, which is this one, which is at an angle. And guys, here there's nothing that we're told about the air resistance. As the hot air balloon moves up, there's an air resistance that pushes the hot air balloon downwards, but there's nothing that we're told about it, so we just ignore it all the time. Same as in the Newton forces and forces. If the friction is not mentioned and nothing mentioned about the friction, you just ignore it. You take it as if it's not there. In most cases, they tell you that they ignore the air resistance, or they tell you do not ignore it. So in this case, there's nothing they talk about. So these are the only forces that are acting there. Now let's go to the question. It says draw a label free body diagram showing all the forces acting there. So the question is 5.1 free body diagram. I'm going to show you two sets of free body diagram, but I'm going to show you the one that is acceptable. In fact, this one that I'm doing is the one that is acceptable because it doesn't have components. It's the force that moves a hot air balloon there, and then we have the gravitational force, and then we have the force of wind there. The force of wind there, and let's say this one, this is the force of what? Of fire. The force of fire, it's the fire that moves a hot air balloon upwards, right? So this is the free body diagram, and this one, guys, it's no longer acceptable because it has components. So don't draw it, but I'll draw it just to show you because it helps you when it comes to calculations. So it's a force of fire there, and then we have the gravitational force. Guys, if the force is at an angle like this force, it's at an angle, it has components. You have your Fy there, and then you have your Fx there. So you have there, you have your Fy, and you have your Fx in that direction. So the wind, it has components there. Guys, this is very important. It helps you when it comes to calculation. So guys, if looking here, you have 50, let's say this is our force. This is the force, and then your vector diagram is that one. So if this is 50, if that is 50, so this will be what? Your 40, because this is what is 90, and this will be your 90 there, and this will be your 50 there, right? I hope that makes sense, guys. So what are we doing now? Let's go to the calculation in 5.2.1. Calculate the work done by the gravitational force. So in 5.2.1, we wanted the work done by the gravitational force there. So it's going to be work done by gravitational force is equal to gravitational force change in y, because this is moving vertically, cos theta. And then it's going to be mg delta y cos theta. And then we substitute the mass. The mass of the hot air balloon is 245. 245 times your displacement is 12 meters cos. And then guys, very important, the direction. The hot air balloon is displaced upwards, and the gravitational force is going downwards, right? So the angle between the two is 180. So here it's going to be cos 180 degrees. So it's going to be, the answer there, it's going to be negative of, because of that. When you punch that in the calculator, you have 28,812 joules, right? Alternatively, guys, what you can do, you can calculate this. Come on. You can calculate this by using this formula. This one. Alternatively, you can say work done by gravitational force is equal to negative change in gravitational potential energy, which is going to be negative mg final minus mg initial. And then the mass, there's a negative, don't forget the negative, 245 times what? 9.8. And then the height final, at that moment, the height final, it's what? It's 12 meters now. It's 12 meters. Initially, it started from the ground. The hot air balloon, it was in the ground, so the initial height was 0. So it would give you the same answer, negative 28,812 joules. I hope that makes sense. I hope that makes perfect sense, right? So now let's go to the next question. Calculate the net work done on the hot air balloon. So the net work done, guys, is calculated by the net force. I'm gonna show you different ways of doing this. 5.2.2. I'm gonna start with the net force. The net force of what? Of these forces. Guys, remember, this is not acceptable as a free body diagram because it has components. You don't draw it. This is the one that is acceptable. But now I'm gonna do the net force of these ones, right? The net force of these, because this is moving vertically, so the net force is going to be vertically. As you can see, guys, more forces are going downwards, so that means the net force is going to be going downwards, but we're going to prove that. So I'm going to start with the net force. I'll say net force is equal to the gravitational force is going downwards, which is going to be negative, and the Fy is going downwards, is going to be negative, plus the F of what? Of fire. See that the force of fire is moving up is positive and then down is negative, those two. That's what I've done there. So gravitational force is going to be equal to mg, and then the Fy is going to be F sine theta, plus, and then the force of fire we are given that one, there's no need to calculate that. Now when it comes to substituting, it's going to be we're going to say the mass, it's negative 245 times 9.8 minus, guys, you need to be very careful here, very careful, because the force is to the angle, this 50 is to the vertical. We use the force that is what? To the horizontal, right? We're going to use 40 in terms of what? 50, because it's to the vertical, it's here, but we need to use the force that is here, so we're going to use 40. But you can use, okay, let me show you. So it's going to be the force of fire and the force of wind, it's 1870, It's 1870, which is this, sine what, 40, plus the force of fire. We were told the force of fire, the hot air, it's 3000. It's 3000. Guys, here you can even use, instead of sine 40, you can say cos. Even though you were wanting y to calculate y, you can even say f cos, but instead of, you use the 50 that you were given. So here in this case, the cos 50 and the sine 40 are equal, right? So you can use anything. You can use any when you want fy. So when you punch that in the calculator, guys, punching that in the calculator, you get negative 603,01 newtons. That's the net force. As the question, it wanted the work net. So having, guys, this simply means that the net force is going this way. As I've mentioned, the net force is going downwards, and the hot air balloon is displaced that way, right? So how do you know that? Because of the negative. Remember, I've anticipated that looking at these two forces that are going downwards. That's not always the case, but I was just anticipating. So the angle between them is going to be what? 180. It's very important. Now, having the F net here, I can calculate the work net using the F net. So I'll say the next thing, work net is equal to F net change in x cos theta. Guys, this simply means that if the F net is going in the opposite direction, that means the hot air balloon is what? Is decelerating. Right? In other words, that means is what? Is slowing down. Right? Okay. Now let's substitute now. Our F net is negative 600, is negative 603 times the change in y. Now remember, it's not y, it's not x, it's y. The change in y, it's what? It's 12 cos 180. Remember, I said it's 180. The hot air balloon is moving this way and the F net is going downwards. So when you punch that in the calculator, your answer there, it will be 72,000. No, not 72,000. It's 7,236. It's negative 236. 200. Guys, I do not substitute the negative here. This negative, I'm not going to substitute it there, because it just shows the direction, and this shows the direction as well. I can't put two directions there and there, just need to put one. So it's negative 236,12 joules. That's the work done. Let me show you another way that you can do this using the work net. So you can say there, work net is equal to change in EK, right? Change in EK, and then the work net there, it's the sum of all the forces, sum of the work done of all the forces there. So which is going to be the force of fire, Fy, Fg, right? So I'll say here, in fact, guys, there's no need for the change in kinetic energy because I want the work net. So I'll just say work net is equal to F, the force of what? The force of wind, which is going to be Fy, which is the component, that is the one that is going downwards, plus the gravitational force, plus the force applied that moves a hot air balloon upwards, right? So the Fy, the work done by the Fy there, so it's going to be Fy, it's going to be Fy change in y, cos theta, plus The gravitational force, the work done by the gravitational force, we already asked in the first question, plus the work done by the force of the fire. This is the force of fire. Force of fire, change in y, cos theta, right? So what I'm going to do now, I'm going to the force, the Fy, it's the 1870, which is this one, it's 1870, so we're calculating the work done by that. So it's 1870 and the displacement is 12, and then cos, no, I'm not doing it right, because the Fy, it's going to be 1870, the Fy, it's supposed to be sine what, 40, and then times by the displacement, which is 12, times by cos 180, because the y is going downwards. The object is displaced this way and the Fy is going downwards, so it's 180, right? Let me push it this way, right? Let me just write it this way, right? I hope it makes sense, guys. What I've done here, it's this part, right? This is Fy only, this is Fy only, and then the displacement, which is 12, and cos 180, just mentioned there, and then plus, it's not going to be a plus, the work done by gravitational force we already calculated, it was negative 28,812 plus, let's put this in a bracket, and plus the force of fire, it was 3,000. Let me put it in the bracket, it was 3,000, and the change in y is 12, and the displacement, the force of fire is going up, and and the displacement of an object is also going up, right? So it's going to be times cos 0 degrees, right? So the work net here is going to be the same answer. It's going to be the same answer, which is negative 700 to 236,12 joules. I hope that makes sense, guys. I hope that makes sense. You can also do this question by using the work done by non-conservative, which is change in EK plus the change in EP. It will give you the same. So what are you going to do here? The work net, do we know the work net is equal to change in EK? So what are you going to look for is the change in EK. Let me do it quickly. So the work done by non-conservative force here, the non-conservatives here, it's the work done by the force of fire plus by the work done by the Fy only. The gravitational force is not the non-conservative, and then change in EK plus the change in EP. The change in EP, plus the change in EP. So the work done by the force of fire, which is this, so it's going to be 3,000 times 12 times cos 0 plus the work done by Fy. I'm just going to copy this. So it's going to be 1,870 sine 40 times 12 times cos 180. Guys, for this, those who understand maths, I'm not good at maths, but I understand the maths part in physics. Here you can simply say here, instead of sine 40 times by cos 180, you can just say cos 130. Okay, let's leave it like that. Okay, so I'm done with this part. So I'm here now. I'm here in this side. So the change in EK, I'm gonna leave it, and then plus the MGH. the change in EP, it's mgh final minus the mg initial, so it's going to be 245 times 9.8. Height final is 12, height initial is 0. So you have here the change in ek, it's going to be negative 7,236,12 joules, right? Since we know the work net is equal to change in ek, therefore this is going to be equal to the work net. So it's going to be 7,236.12 joules. Hope that makes sense. Let's move on to the next question. The next question, it says state the work energy theorem. The work energy theorem, guys, you can define it by the work energy theorem that says work net is equal to change in ek. The net work done on an object is equal to the change in kinetic energy of an object. Now in 5.4 it says use work energy theorem to calculate the velocity of the balloon after it has risen 12 meters. So we want the velocity at 12 meters. There. Let me push this down. Okay. Right. So it's 5.4, the last question. So they said we should use work energy theorem. So we'll use this work energy theorem, alright, to calculate that after it has risen. So guys, we already have the work net, so we just want the velocity. So we'll say half mv final square minus mv initial square. And this is our work net. And then we'll just substitute the work net here. So it will be negative 7,236,12 is equal to half the mass is 200 is 200 and what? It's 245 the mass, and the final velocity is, that's the final velocity that we want, right? The initial, we were told it's what? It's 15. So it's moving upwards at a speed of what? So that's a speed that it moved from the beginning, from the ground. This is the initial velocity. So we'll say 15 square, right? So if you do the math here, so if you say this, so if you punch that in the calculator, you say half times 245, it's going to be 1,122,5. 122,5 times the VF is going to be 122,5 VF squared, and then you say 122 times by 15 square. It's a negative 15 square. So it's going to be negative 27,562,5. And then you have this 7,236,12. And then when you do your math now, it's easy. These are the like terms. So you put the square root on the VF and you divide. And then your final answer there, just to save time, guys, it will be 12,88 meter per second. That's your final velocity there. I hope, guys, this question makes sense. Cheers, bye.